The next presentation, the third presentation of the day, is actually the evolution of high-performance spring probes. And our speaker is Bert Brost from Technoprobe. He's a senior manager with Technoprobe USA. He started his career in engineering with microcomponent technology, where he designed test electronics. With more than 40 years of experience in back-end test, Bert has held senior management positions with Multitest, Johnstick International, and Control Data Corporation. Bert holds several undergraduate degrees and an MBA from the University of St. Thomas, Minnesota. Welcome, Bert. Please go ahead with your presentation.
Thank you for that nice introduction. Yeah, thank you, everybody. I appreciate your taking the time to be here today. It's late in the afternoon in Europe and early or late in Asia. But here in Minnesota, it's always blue skies and sunny. So today we're going to talk about the evolution of high-performance spring probes. And let me get started. So we're going to cover a lot of ground today. As you can see, we're going to talk about the challenges and opportunities in developing spring probes, some of the measures. We won't do the deep dive Gert did. That was a great presentation, Gert. We'll talk about microcomposite MEMS. As a lot of you know, I've been exploring MEMS for spring probes for probably 8 years now. Spring probe stress versus travel. We'll take a look at pointing accuracy factors. We'll do a little exercise in calculating pointing accuracy, and we'll talk also about probe receptacle concentricity, which can lead to a pointing accuracy offset. We'll talk about MEMS tips alloys. As Matt said earlier, gold can be somewhat sacrificial, and you'd like to have something that's hard and highly conductive to give you that long life. We'll talk about contacted solder ball witness marks as a demonstration of pointing accuracy and repeatability. And then we'll wrap it up. And I didn't do this alone. There's a number of contributors. We'll talk a little, we'll give them credit as due. So challenges and opportunities. It's always been pretty much the same. DC, contact resistance, leakage signal path resistance, probe current capacity. And as Kurt described, there's a lot of discussion on how to measure and report the constant current carrying capability of a probe. Do you do it pulse? Do you do it in a destructive test? Whatever. So I appreciate your deep dive on that, Kurt. AC electrical, bandwidth, capacitance, crosstalk, rise times, etc. Those eye diagrams shown by Matt really speak to the overall AC characteristics of a probe. Mechanical alignment, planarity, contact force, pad, bump, ball size, pitch, and layout. As everything is getting smaller, that is, pitch is shrinking, and bumps and targets, balls are getting smaller. We're looking at how we can bring the front end of probe heads developed by Technoprobe to the back head with contactors manufactured by probe head. And by the way, we don't do sockets. We do high-performance test contactors. The environmental issues, temperature, pad damage on the load board, lifetime or number of touchdowns on a spring probe. The path forward, as we all know, higher power. I was on a call the other day where people were talking about they're not able to test all the functionality of their device at the same time because of the power demands and the heat dissipation. Increasing I/O density, pitch shrink, number of I/Os continue to increase. Higher system integration, smaller devices, and again, thermal. And then we're bringing hand test, manual test, to sub 400 micron pitch applications. And as always, we're looking at how we can bring costs down for our customers while increasing their throughput as measured in first pass yields. and number of devices tested per hour. So some of the measures, you've got to have measures. If you don't have measures, you just don't know where you're at or where you want to go. So it's all about repeatable contact force. Right now, short probes are in vogue because of the electrical AC parametrics, large overall travel, which seems to fly in the face of going short. So we want, to have 1 millimeter of over travel on a probe that's 0.5 millimeter tall. I don't know how we do that. Long lifetime, effective cleaning methods. And again, back to Matt's point, you really want to have good cleaning methods. I know there are a lot of abrasives out there, a lot of chemicals and brushing, but abrasives do change the geometry tip, and in gold, they will wear off the gold plating. So it has to be easy to maintain. That is, easy to set up, easy to tear down, and easy to rebuild. Electrical high bandwidth for functional tests and AC tests. Low noise on signal, power, and ground. That's back to looking at those eye diagrams. Where is that signal in place and time? And is it buried in noise? Because if it's buried in noise, your test instrumentation can't find it. So low resistance for DC measurements. Again, what is that IR drop at the point of contact with the device, at the load board, and the interconnecting components of your spring probe? Then there's high current capacity for power delivery and DC parametric tests. Kelvin probes for analog and mixed signal. This is where you need those high performance DC measurements when you really want to take a look at the gain of an amplifier, the offset error between inputs of an amplifier, or you're looking at mixed signal devices and you're really concerned about least bit significance when you're converting an analog signal to digital or vice versa. So these are the things we're thinking about as we contemplate the evolution of high performance spring probes. So for us, and like I said earlier, MEMS have been something of interest to me. So we're building probes using MEMS technology, MEMS micro electromechanical systems. And we're using a 3D additive MEMS process. Shown here on the left is a medical instrument. This instrument is inserted into veins. And then those little clampers do whatever the doctor wants them to do. And we won't go there. But if you look at the picture right next to it, that's a cell phone. And that's that same part scaled to that cell phone. So we can really get into super miniaturization with very, very tight interconnect tolerances within the spring probe and the overall geometry of the spring probe to the device under test. So we're pretty happy with this and our early results. And, as Ira said, IoT is a big thing, and MEMS are big in IoT. So this is a great process that's enabled us to produce a new structure, thus creating a new and exciting contacting solution for both front-end and back-end tests, okay? So that's it for MEMS. We'll jump into the product. So this is a stress analysis of our first generation MEMS spring probe. We're going to beta with this probe. We're pretty excited about that. It's a one-piece probe. And what that means is we contact at the DUT, and then we have our spring and our body, and we contact at the test interface board. The lion's share of the current flows through the body, not the spring. And here's just another example of the stress. So right now we're at 300 micron pitch, and we're going to get smaller and shorter. So one of the neat things about our probe, as you can see, we're using a serpentine spring, and they're very linear, and they don't twist like a coil spring. So as we're compressing this probe, there is no radial motion translated down to the test interface board pad. So the test interface board pad remains pristine over hundreds of thousands of insertions. So that's all part of this.
Bert, sorry, Bert,
yes,
sorry, a quick question on that,
yeah,
on that picture.
okay.
Isn't there an offset between in the previous slide?
No, there isn't.
On the Dutch side and the test interface board contact, there is no offset?
No, this is just an electrical schematic. This is not a mechanical representation. As you can see, the tip of the probe, and on the next slide, we'll see the distal end or the load board or device test board are on center. There is no offset.
So it is a concentric thing rather than an off center. Okay.
Yes, that's a great question. Thank you. So as to your question, you can see it is definitely an on-center probe.
Mm-hmm.
So pointing accuracy here for us, it's defined as a radial target, radial true position accuracy, as in GDT tolerancing, okay? And so what that means is you're going to have an axis, a center point, and you can move in an XY from any direction on that axis. And that gives you the diameter of the target you're going to hit, plus the radial direction from the center. Now, the primary factors affecting your radial target size are the extended length of the plunger, as shown here from the barrel, okay, along with the retained length of the plunger in the barrel, and then the working clearance, which I'll show later. The working clearance between the plunger and the barrel. In our case, we have a body. We don't have a barrel. As you can see, what we've got here is one continuous two-point contact, which really works in the favor of people who need repeatably low contact resistance. Okay, so let's move forward. So if you want to calculate the pointing accuracy of your spring probe, there's a formula we typically use, and that formula is shown here, where we take the extended length of the plunger from the barrel, and we divide it by the retained length of the plunger in the barrel, and we take that quotient and we add it to 0.05. And then we take our working clearances, C1, C2, to get C. And then we take C and we multiply it by the quotient of 1 divided by 2. And that gives us our radial target true position. So it's just basic mathematics and basic physics. How much surface area do I have here holding this thing in a straight line? And how much wobble will I have on the outside? So, and as these probes get smaller and smaller, this is very, very important. How much meat? How thick is this? How will it maintain its concentricity when hitting the balls without providing lateral forces that can damage and even shear balls? So that's all important. So we can do a hypothetical. We've got a hypothetical probe here, and we've got some hypothetical numbers. And I just kind of pulled these right out of the air, right out of the air. So let's say the extended length of the plunger is 0.1 millimeter. And then the retained length is 2 millimeters. And then we have a working clearance of 0.001 millimeter. So if we work our formula, we go through this and we take 1 and we divide it by 2. And then we take the quotient and add it to 0.5. With that work done, now we can take 1 divided by 2, take the quotient of 0.5 and multiply it by 0.001. And we get this broken down formula, 0.0005 times 1.0. And that gives us a radial true positioning of 0.5 microns. And that means that within a circle that has a diameter of 1 millimeter, I'm going to repeatably hit within that circle. Now, if I have we'll talk about this in the next slide. I'm getting ahead of Bert. So then there's concentricity. And concentricity is affected by the manufactured hole in the receptacle or the contactor body. We don't have test socket bodies, we have contactor bodies. So, and these are precision machined, okay? So what we do is we take a look at this here. We take a look at the extended length of the barrel. That's this. We take a look at our contactor hole width. And typically what all manufacturers of contactors, test sockets, and probe heads will do is they will manufacture this hole with a very tight tolerance, creating a snug fit for that probe, because we want it to be field replaceable and we want it to be easy so people can slide these probes in and out. And when they're sliding them in, we do not want to create an environment where the probes are damaged. So the high performance contactor manufacturers that sponsor TestConX and our company create a real tight, snug fit. So these probes won't lean to the side. And that's based on the body width, as I mentioned earlier, and contact or body thickness. That's the amount of material. And this creates a challenge for us as we move forward, because as the probes get shorter, so does the contact body thickness. And that introduces other challenges. For example, if I'm doing a 2000 ball device and I have a really thin body, watch out, because you could have contactor bowing unless you take the time to analyze the forces and create the proper frames and stiffeners. You will bow, okay? That's just a given. So a word to the wise to customers and suppliers, make sure that you're taking a look at the combined forces and designing to maintain a very flat, multi-site probe head or high pin ball count contactor. It's just a given. So one of the things, if this were leaning sideways, okay, that would create a contact offset. That means this would be over here, okay? That is an offset from my ideal position. Well, my radial true position or diameter won't change of where I make my witness marks on the bumper ball. That'll stay within that theoretical 1 millimeter we had. It'll be over here if this is leaning in any direction, or over here or wherever. So you want to keep this probe as perpendicular to the test interface board and the device under test as possible. So there are other things that we're looking at as we bring the back end and the front end together. And that is the use of probers and optical alignment systems. And the real challenge with probers and spring probe is the optical alignment to the probe tip. And new algorithms are being written all the time to deal with that. But because you have a round probe, excuse me, in a round hole, the probe will rotate in that hole, which means finding those probe tips and then using them with a static algorithm becomes very difficult if you're trying to determine your central axis for contacting. In the evolution of spring probes, what we're looking at are different solutions for maintaining a highly repeatable alignment system of the prober to the probe for accurate and repeatable contacting of contacting of bumps balls, and pads with pitches less than 300 microns. And we're talking about applications now at 150 microns. So, and less, people are asking about. So, and we've got some 150 micron applications we're doing with manual actuators and other things. But our spring probes right now are targeted at the 300 and sub 300 micron market. So what we've done to address the issue of probe rotation in the contactors, we've created a probe that isn't round. It's a rectangle, it's a square. So if you take a look at it, and this is just a rough illustration here, this probe won't turn in this hole. So these tips are always going to be in the same place every time. So the prober can find these, lock in on these, and set its algorithm so it knows where the tips are, and it knows where the bumps or balls are on that WLCSP device or wafer. And so we get great alignment and great contacting. And as Matt so eloquently said, gold tends to wear off, but what we can do with the MEMS process, as we can do additive layers at the tip with super hard, highly conductive alloys. And these alloys are homogeneous, as Matt described. So we don't have to worry about intermetallic migration, that is the tin alloys combining with the gold to create a third alloy. And because they're hard, most people who are using rhodium or palladium or those other things tell you they can go for thousands of cycles and then only brush off the debris in test. And we're finding the same thing. So yay to Matt for bringing that to the surface. And, you know, it's always been kind of a guarded secret that probes plated with about 50 microns of gold, the gold is sacrificial. You keep bumping that gold, a soft material with a harder material, and it's going away. And the first time you use an abrasive to clean that probe tip, you've started to remove the gold and change the tip geometry. So I think as an industry, we need to look at using harder, highly conductive, homogeneous materials at the tip that give us that great, repeatable, low contact resistance. So that's Bert's recommendation. The opinions expressed here are not those of TestConX, but of Bert Brost. So one of the things that people have been talking about that's important is maintaining force. The force is what provides the surface stress of the probe tip to the contacting surface on the ball. And it's that stress that allows you to break through the oxides and get to that pristine plating material. So you want to have a very repeatable stress at the ball from device to device, so you're ensuring a good electromechanical connection at the device. And that's all based on what's providing it, this force of the spring. So with the MEMS serpentine spring, we've done a number of tests up and over 1 million. This happens to be at 800,000 touchdowns. But what you see here is stress at 800,000. These are samples. And this is our force. And we recommend about 350 microns of over travel with this particular probe. It's about 5 millimeters tall. It's our tall probe, and it's being used in a special application for somebody. They wanted tall. And we're getting about 8 grams of force. So you can see insertion, return, insertion, return. This is that same probe at 800,000, but in a larger hole, okay? It's still a very snug fit, but it's the distribution's a lot tighter. Both are very acceptable in any test application. We were just wondering about how the friction between the probe and the hole influence overall forces, because I don't know that anybody's talked about that in the past. So we took a look at that, and that was pretty good. And again, this is just, pushing down and measuring force. It's the typical test setup where you put the bottom end of the probe, that would be the DIB side or test interface board side, on a plate. You use a pin to push down on the top, and then you have a servo motor with great resolution and a load cell. So you're measuring force as you're pressing down or doing a touch on the probe to a controlled limit. So that's that. So as I mentioned,
Sorry, before you go there, may
yes.
I ask you a few questions? We got two questions, which was
related
to you showed us the formula on the kind of the accuracy. The question was on, were you able to validate the formula on actual measurements?
Yeah, we'll get to that.
Okay, so we'll get to that.
Yeah.
The second one is actually on the electrical path. Is the electrical path length increased due to the long continuous MEMS spring that doubles as the signal path?
It's a parallel circuit, okay? While it is a continuous path, this plunger does go up and down in the body that it's connected to. So what we have is the lion's share of the current flow through the body and not the spring. And to what Gert was speaking to earlier, it's all about temperature. And we want to minimize the temperature of the spring to maintain spring life. Now, unlike stainless steel or music wire springs, we're able to use an alloy that has, how can I say this, has greater resilience over a wider temperature range, as well as without going plastic on us. So, and that's a proprietary alloy that I can't share at this time. So.
Okay, that's a proprietary alloy for the spring, you mean, right?
Yes.
Okay, all right. There's another question. How long is the longest possible probe possible? And how short is the shortest possible? So basically, the max and the minimum length of the probes.
Oh, I'm not sure what our minimum is, okay? But obviously, everything's getting shorter as we're looking out past 50 gigahertz, and everybody's talking about 6G. So right now, we're saying that we're going to go out to a probe that's probably 1 millimeter tall, and then see how we do there. Okay, that's our roadmap. And with regards to height, we're working on a large 70-site application where the spring probe is over 6 millimeters tall. So with the MEMS manufacturing process, we're really not constrained. The big constraints will come in with regard to the ability to physically handle these. And that's where we're going to have to introduce robotics for probe head and probe card assembly.
I see. This is for the as low as the 1 millimeter case.
Yes.
Okay.
And the 0.5 millimeter, if we get, and that's on Bert's roadmap. That's not on the company's roadmap.
I see. That's on Bert's roadmap.
Yes.
All right. So, what is the high temperature specification and the cold temperature specification? Again, this comes down to the highest and the cold.
Right. We're targeting minus 60, excuse me, to greater than 160. We're going to be evaluating our probe at plus 175 C for automotive applications. But right now, we're speccing a window of minus 60 to minus 160.
You mean minus 60 to plus 160? Right?
Yes. Yeah. Okay. Yeah. Excuse me.
Yeah. No problem. Okay, that's good. Then, how do you retain probes in the socket body? And the question is, I do not see any flanges on the probe, how do you
Okay.
guarantee a constant electrical contact with the probe card?
Well, there's a couple ways you can do it. Again, since it's a MEMS process, we can add any feature we want to this as we build it, okay? It's not like we have to go out and buy die for making barrels or turn plungers on a lathe. It's 3D printing, and the beauty of 3D printing, we can make it any way we want. We can put larger shoulders up here if we choose to. Typically what we'll do is the head will be slightly smaller than the body. And then we can use these shoulders up against the top of the body housing, okay? The other thing we can do is put a retaining feature down here where we might have some kind of, say, spring, potentially, where when you push it into the body, the spring compresses, giving us a friction fit. Friction fit not enough to lock the probe in place, but enough to give us a really good preload. So we have a lot of options because we're printing these things. We're not deep drawing barrels. We're not turning barrels. And we don't have to worry about plating the inside of a barrel. You know, that's always been a huge challenge, is how do you get that gold plating inside of the barrel? So we're not worried about voids in the plating inside of the barrel and or different surface roughness irregularities. Does that answer your question?
I think it does.
Okay, thank you.
Thank you. Are you able to produce a higher force, 20, 30 grams with MEMS spring?
Yeah, we do that by design. And when we're designing the MEMS spring, we have proprietary software for modeling the forces, okay, with regard to how the spring is printed. So yes, we can do that.
So proprietary software is using the modeling for the stress, and that's how you are actually coming up with the forces?
Right. We work with Microfabrica in California.
Uh-huh.
And Microfabrica has developed over the years special software for 3D MEMS printing. And I don't want this to be a commercial for Microfabrica, but that software allows them to simulate what a 3D MEMS spring might do before they actually print it. I apologize, Ira, if that turned into a commercial.
Okay, so the next question is, the homogeneous MEMS tip are made of alloy. Is it one piece part with the plunger?
We can do whatever we want. We can put, say, hypothetically, we can put rhodium as our first two surfaces, and then right behind the rhodium, we can put gold, and we can run gold the full length of the probe. So we've got the best of both worlds. We got very hard with gold right underneath it, or we can put silver underneath it, which is even a better conductor. And since it's covered, we don't have to worry about the oxidation of the silver.
Okay, great. Could you explain more how a spring function works?
Yeah, it's there's no secret that when you're doing MEMS, your springs are typically a serpentine spring. They're not a coil. So when designing this probe, we had the option of doing the probe in its free height, the spring could be compressed. And then when you push down on the tip, the spring could go in the expansion mode, which is a much more controlled environment, because when you're going into the expansion mode and holding it in the body, you have a lot more surface to surface contact with the MEMS spring and the body, where when you're compressing a coil spring, It's not deterministic like the serpentine is here. When I say not deterministic, the amount of surface area contacted by the spring in a traditional spring probe is somewhat random, whether the spring be on the inside of a barrel or on the outside of the spring probe. So we can calculate for that as well, design and manufacture to that with the MEMS process.
Okay. What's the pricing in comparison to current single probe?
My answer to that question is RFQ. We're happy to entertain any requests for quotes. We'll give you all the pricing you want.
That's I'll steal that answer from next time.
Okay, thank you. No, we're competitively priced. It's not high-end skim pricing and it's not low-end anchor pricing. We're right in the middle. So, okay. And it's a real value-based pricing. We understand we could ask for more based on the value, but we're not.
All right. Are you using MEMS technology to make the bodies? Are the holes in the bodies round or rectangular?
No, Technoprobe Italy has great manufacturing skills with polymers and ceramics. So we're using polymers and ceramics, and we can, through technology developed by Technoprobe for its probe cards, we can machine rectangular and square holes just as easily as anybody else can make a round hole. And we can do that in all kinds of ceramics and polymers with tight resolution and great feature definition.
Okay. The next question is the mechanism to show the spring function available?
Yeah, it is in another presentation. Yes, it is. And we're happy to show that too, but not today.
Okay. All right.
I didn't include it in the presentation, or I'd show it to you. You know, in the one slide where we do the surface stress, you could kind of see it, but that's not a good representation.
We have a very interesting question, Bert, here. Bert, what feedback can you give the market with your interconnect roadmap outlook or look like when it comes to dealing with the SLT market, testing ICs at 800 watts or higher with test times of 1 to 3 hours? How robust is your contact over time in these cases? I think it's very interesting, especially because since you're defining a new market,
right?
This would be a very interesting and I can relate to that question very well.
No, I mean, there was a time when I thought 5 watts was a lot. All right. So Gert did a great job talking about temperature rise across the probe. And now we're putting the probe in an environment where the contact and everything has a heat dissipation requirement of, like you said, 800 watts. I mean, you can light up a baseball field with 800 watts. So that's when you have to take a more systemic perspective. You can't expect the contactor and the spring probe to dissipate 800 watts for you. You have to take a systems approach, and you have to have complementing components in there that'll help with the heat transfer, that is pulling the heat away from the device. In your PCs, you look inside, there's this huge fan sitting on this huge block, okay? And those solutions have to be portable to test. We have to be able to control temperature at the device under test with a systemic solution. Whether it's some kind of gee-whiz thermal streamer or it's surface-to-surface platen contact, pulling the heat away. Heat transfer now is a big topic. I worked with a guy years ago named Harlan Fowler, and Harlan amazed me with his thermal calculations and even the presentations he gave here at TestConX. I mean, this is a subject that needs a lot more attention. So if you really, I mean, if you go back in the TestConX archives and look for papers by Harlan Fowler. You'll get some good answers.
So I think if I took the answer, you still see the role of the MEMS probe there, but you still need in order to achieve the 800 watts or the 1 to 3 hours, you're thinking of a more systemic solution besides
Yes.
fuel effect. Okay.
Exactly.
So there's a question on, do you have any idea on the RF frequency, signal responses, etc.?
Okay, our 5 millimeter probe, as tested in our lab in Italy, is excuse me, let's fall back here, is at 8 gigahertz at minus 1 dB. That's ground signal, signal ground, and ground signal ground. It's at roughly 12 gigahertz at minus 1 dB. And that's our tall probe.
So it was 8 gigahertz at minus 1 dB, and I missed the 12 gigahertz.
Yeah, and those are the difference between ground signal, signal ground, and ground signal ground.
Okay.
So, and we have a very impressive RF lab in Italy, and so they're working with us on this.
I see. There's another person who just wants to especially thank you, Bert, for a wonderful presentation.
Oh, well, thank you. Thank you very much.
And the speaker, the person who sent that note, I couldn't get the name, but it was just a special thanks to you. Okay. And then there's another question. Bert, what is the smallest pad size and pitch that latest MEMS technology you can have especially done for catering to that situation?
Okay, right now, 150 micron ball size. So that's our smallest ball to date, 150 micron. Of course, we're pushing Bert's pushing for smaller balls, and our design team is responding with very interesting and innovative ways to do that. But right now, about 100 micron ball.
Okay. Let's see. I think those are the questions I had. You can go ahead with your presentation, but this was a very good one because people were flooding with you beautiful questions.
Well, that's encouraging. Thank you.
Yes.
So
I think you did finish that slide, right?
Okay.
The one
so
not this one. I think you had to go back.
Okay, yeah, we were just talking about, I think we pretty much wrapped this up with the questions and everything else. So we'll just go to some. So I did have balls at 100 microns, like I said, but I didn't have really good pictures of them. And in hindsight, I should have added them to this. But what I show here are balls at 250 microns and 200 microns. And then what we did is as you can see here on the far left, one touchdown on these bumps or balls. It's a bump on a wafer is what it is. We bought these wafers with bumps. And then the 200 microns. So this is where we're contacting relative to the axis, and the axis in this case is just refracted light, okay? So then we came back after 5 touchdowns to see how repeatable we are, how accurately are we staying within that radius true position, that diameter. So this is after 5 touchdowns, and this is 1 touchdown. 5 touchdowns, 1 touchdown. I sound like the optician who goes, lens A or lens B? No. Anyway, so this is 5 and this is 1. So you can see it's a very, very repeatable. This is the SolidWorks of the probe tip that we used. And as you can see, this one's is layered, where you could have the rhodium, highly conductive, and palladium if you wanted. Any mix and match. I mean, it's kind of like the buffet with the MEMS manufacturing process. So in conclusion, I think everybody said this during the test conference and will continue to say this. We live in a time of great change. I mean, I can remember when I was excited with a 300 baud modem printing at home in the dining room, and here I am video chatting with people from all over the world and presenting slides in real time. So with that, MEMS, I feel, and this isn't my first time to TestConX talking about MEMS and probes, opens an exciting world for us. We can hold the tolerances so much tighter than we can with other manufacturing processes, as well as the manufacturing repeatability. So that really opens the door for low cost, high volume WLCSP fine pitch test in multi-site or single site test applications. We're continuing our innovative work to make this technology an increasingly effective means for increasing throughput. And that's what it's always been about, how we help our customers get more good parts in the box at the end of the day without excessive guard banding, without excessive cleaning, and all of that. You want to test your parts to the spec. You don't want to have to test your parts to the spec of the probe. So, and I think the premier sponsors for TestConX hold that to be true as well. So with that, I'm going to move to, so I don't do all of this alone. I got a really strong team that I'm a part of and proud to be a part of. At Microfabrica, I have Arun. In Italy, I have Emanuele. I also have Giuliani. I have Mike Dang in California. Ming Ting. I have Nadia. And I have Sean, all members of the A-team MEMS Spring Probe. And then we have cross-functional supporting teams. So my thanks to them. And thank you all for giving me your time and attention today. As always, I'm very proud to be a part of TestConX. Thank you.
Thank you, Bert. I don't see any more questions. I think you took the maximum questions in the earlier time. So thank you very much. Thank you for the beautiful presentation.
Once again, I would like to very much thank our sponsors who have made this event possible with their generosity and have also made it free to attend. Our premier sponsor, Kohu, our emeritus sponsor, Johnstech, our honored sponsors, ISC, iWind, and TSE, and our distinguished sponsors, Backer Hotwatt, Innovative Circuits Engineering, JMT, Nidec, SVTCL, R&D Altanova, UI Green, and our exhibitor sponsors, ELES, MJC, Phoenix Test Array, and Smiths Interconnect. Please, when you have an opportunity, thank them for sponsoring and making this event possible. And once again, we'd like to thank our premier sponsor, Kohu, the market leader in test interface solutions for the most challenging applications, and ISC, the global #1 total test solution provider. And with that, I will thank you all for joining us today and look forward to seeing you back here tomorrow. So thank you again for joining us and have a good day.
Thank you all.